Thank you for introduction. My name is Hikaru Morita from Shibaura Institute of Technology. I'm going to talk about validation method to improve behavioral flow on UML requirement analysis model by cross-checking with state transition model. Here is the outline of my presentation. First, I will introduce the background and issue. Second, I will describe a method we propose this time. Then, actual case study, and finally, I will conclude with a summary and future works. Let me begin by talking about background. In recent years, a system that provides service is often complex, like autonomous driving system, delivery management system, and route search system, and it is linked with various hardware and other systems. Due to the diversification and complexity of systems, the number of elements to meet the requirement increases, and the necessary requirements are often omitted. When developing such a system, what is most important as requirement specifications? Answer is creating the system that customers really want. In order to meet this, it is important to repeat validation at an early stage in the system development process. That is in the requirement analysis stage. As an example of validation in the requirement analysis stage, we show the following two studies. The first is study of model-driven development using UML model to define requirement specifications. This is also being studied in our laboratory and doing validation of inconsistencies between models and conversion to a model of the design and implementation stage. The second is study of Tariq and Leif. This study is similar to our approach and transformed the activity diagram created in requirement analysis stage into a finite state model suitable for model verification tools. Hence, reachability and security are guaranteed by formal verification. However, although these verification methods can confirm the validity of the service procedure described, any excess or deficiency in the user request cannot be verified. As shown by the red and blue circle in the figure, the defined requirement specifications do not always satisfy all user requests, and may also define specifications other than user requests. Therefore, it is important to verify the excess and deficiency of requirements. In order to judge the excess or deficiency of the requirement specifications, the requirement specifications need to be interpreted from multiple perspectives. In addition, the requirements that are truly needed must be identified based on the difference. As multiple perspectives, this study uses two kinds of different complementary behavioral models in UML. As two kinds of behavioral models in UML, this study uses activity diagram and state machine diagram. Activity diagrams are suitable for defining the entire system workflow, which includes coordination between subsystems. On the contrary, the state transition model organizes the requirements that the subsystem should satisfy based on the state that the system should assume. Therefore, it can be a test case of requirement specification defined by the former. From here, I'm going to explain the requirement analysis model and the evaluation model. First, I'm going to explain the requirement analysis model. We call the workflow defined in the activity diagram and the class diagram, which is the data model together as the requirement analysis model. A workflow is beneficial for realizing a service that utilizes the use case of each subsystem. To achieve the system goals, the data exchange that is required to satisfy the service goals at each subsystem boundary must be clarified. Each partition in the activity diagram represents each subsystem and the users, and the set of use cases of each subsystem is described within the partition. Consequently, the cooperation between all users and subsystems is clarified, and the service procedure of the system is correctly defined. In addition to defining behaviors with activity diagrams, it also clarifies behaviors related to the data defined in the class diagram. In such behavioral modeling, the procedure of the required function can be easily understood from the control structure. However, as the change in the state of the system due to the action is unclear, it is difficult to determine all the states that the system should assume. Next, I'm going to explain the evaluation model. The state transition model defines the behavior by changing the state of the state system by external or internal events. It is easy to understand whether the system requirements are comprehensively analyzed by specifying the state name. However, it is difficult to confirm the execution procedure of the system function and its relationship with other subsystems. Based on the explanation so far, we propose the method shown in the figure. First, the state transition model is extracted from the requirement analysis model. Next, the excess or deficiency of requirement is identified by comparing the extracted model with the evaluation model. Finally, feed back the excess or deficiency of the identified requirement to the developers. In this study, we have developed a tool that automatically performs extraction, comparison, and feedback. By using this method, validation can be performed from multiple perspectives. From here, I'm going to explain the procedure of the proposed method. First, let's talk about the extraction of state transition model. The state was extracted from the requirement analysis model by focusing on the workflow, control structure, and actions. The extracted state transition model is named as the extraction model. The figure on the slide shows the conversion rule from the requirement analysis model to the state transition model. Based on this conversion rule, create state transition model. Next, I will explain the validation. Validation of the extraction model is done from three perspectives. First, number of states when the state of extraction model is classified according to the particle state of the evaluation model. Second, number of transitions between classified states. Third, description of state operation, state transition events, guards, and actions. In this slide, I talk about the overall flow of validation, and from next slide, I will talk about three perspectives. As for the overall flow of validation, first, create an extraction model from the workflow and classify the state of the extraction model according to the evaluation model. After classifying the state, compare the number of states. If the number of states is different, modify the workflow and extract the states again. If the number of states is the same, the number of state transitions is compared. If the number of states is different, modify the workflow. If the number of transitions is the same, on the next layer exists the state of the extraction model is classified based on the next layer. If the next layer don't exist, description is compared. When all the description contents are associated, workflow validation is completed. From here, I will explain the classification of state and the comparison of the number of states. The extraction model have not the layer. For this reason, the extraction model needs to be classified according to the particle size of the evaluation model. In this study, there are 3 steps to classify. First, classify according to precondition described as state name and the operation described in the states. Next, classify by the event cloud action described in the state transition. Finally, classify using external transition based on the state before and after the transition of the states. After this step, the extraction model is classified into the first layer in the evaluation model, such that the number of states in this layer can be compared. Considering this difference, we can identify the following problems. A. Among the states of the extraction model, a state exists that cannot be classified. B. The extraction model does not contain a state that corresponds to the state of the evaluation model. C. The extracted model does not contain a state name that includes the state name of the evaluation model. Developers discuss each problem and modify the workflow. After modifying the workflow or the evaluation model such that the number of states is equivalent, the number of state transitions of the modified extraction and evaluation model are compared. If the numbers differ, then the behaviors of the transitions are compared to identify the transitions that can be considered the same. The remaining transitions in the target state, including some internal state transitions, must be compared to determine whether their combinations are the same. In this case, the workflow transition condition may be ambiguous. Therefore, some action must be added. For all layers of the evaluation model, the previous steps are repeated to improve the workflow based on the observed difference. The improved extraction and evaluation models become a state transition model in which both the state and transition are equal. After the number of states and the number of state transitions are the same, the word and the phrase described as state action, transition, events, guard, and actions are compared. This comparison determines the excess or deficiency of behavior and identifies difference in word expression. Then, I indicate a case study. This method was applied to the automatic baggage transport system, which is a PBL task in our department. This system is a parcel delivery system that links to autonomous vehicle type robot with 6 subsystems, a relay station, headquarters, a reception desk, and the recipient house. Figure shows the circumstance and the relation between all subsystems. First, the workflow of this system is defined as a cooperation model of 6 subsystems. Left figure shows the extraction models generated from the workflow of the relay station based on the extraction rules. Right figure is an evaluation model that defines the requirements of the relay station as a state transition model. The orange box in left figure shows the classification result based on the process outlined in state classification for the evaluation model. In this case, as a result of the state classification, the number of states in the first layer is equivalent to that in the evaluation model. However, as shown in left figure and right figure, the number of transitions between waiting to walking with delivery robot differs. Comparing the state transitions inside both states, it was discovered that the difference in the transition branching is caused by the path surrounded by the dotted line in right figure. Comparing the state transitions inside both states, it is clear that the black transitions have the same meaning. However, because the remaining two transitions have different transition branches depending on the path surrounded by the dotted line in right figure, a difference in meaning is generated. Figure of before shows a part of the workflow corresponding to the two blue lines in the extraction models. This can be automatically identified from state based on the conversion rules. Reviewing the workflow, it was discovered that the branching condition can be read from the branching process flow. But the branching condition based on the delivery state value specified in the evaluation model was not specified in the workflow. Because the design model for the final program will be derived from the workflow, the processing procedure should be described in clear terms at this stage. Therefore, the workflow was modified as shown in figure of after. Next, we consider the transition marked in red with states S10 and S12 as transition sources. The workflow defines the behavior of delivery completion, but the evaluation model does not include a behavior equivalent to delivery completion. As the initial requirement includes the behavior at the time of delivery completion, it is clear that the evaluation model is insufficient. Right figure shows a modified evaluation model. The part surrounded by the red dotted line in right figure denotes the added state and state transition. After the first layer was modified, the extraction model was regenerated. It was observed the number of states and transitions in the first layer was equivalent in both models. Subsequently, the same classification was performed in the second layer. It was observed that the number of states and transitions in the second layer was also equivalent in both models. As a result, the improved extraction model and evaluation model are state transition models with equal state and transitions. Finally, we compare the word of the event, guard, and action, which were the behavior of the transition or the state and determine the excess or deficiency of each behavior. In reference to the walking with collecting robot, state shown in left figure and right, the four behaviors can be regarded as having the same contents, but the behaviors circle In red shown different expressions. As the expression in the evaluation model was considered to be better, the expression of the action in the workflow was modified. Furthermore, it was discovered that the behavior order was different. The order in the evaluation model appeared to be more appropriate. Therefore, the order of action in the workflow was altered. Next, we focus on the working with delivery robot. State shown in left figure and right. The execution model did not exhibit the behavior corresponding to the behavior circle in blue in the evaluation model. Because the behavior was insufficient, an action at the part corresponding to the relevant state of the workflow was added. Moreover, in the extraction model of left figure, the blue underlined behaviors aim to update the delivery record such that the representation is modified more clearly. Figure of after shows a workflow that reflects these modifications. The actions shown in pink in figure of after represent the added and modified actions. Here, I'd like to summarize this study. First, when there is a difference in behavior between required specifications from different perspectives, you can clearly define action and conditions. Therefore, you can be defined without omission of requests. For behaviors with the same contents but different expression, you can discuss which expression was easier to convey and clearer. In design and implement stage, you can prevent the interpretation from being different. Other future works. Application of proposed method in requirement analysis model and evaluation model described for each use case. Experiment with objects that transition through the workflow subsystem. I plan to do these two things. This concludes the presentation. Thank you for your attention.